Hi, we're Emily, Jessica, and Cindy, to be graduates of Doherty Valley High School and Cardackley's AP Calculus BC class, A period, 2017. We've been seeing a lot of these Draw My Life videos over YouTube and social media, so we decided to do something similar, except this is going to be called Solve My Life. In this video, we're going to be talking about logarithmic functions and the differentiation of logarithmic functions.
First off, what is a logarithmic function? In mathematics, a logarithm is the inverse operation to exponentiation. So, the inverse function of f of x equals e to the x is the inverse natural log of x. When writing logarithms, you have a base and an argument. For example, with log base 2 of 5, your base is 2 and your argument is 5. For some simplification, log base e of x is often written as natural log of x, and log base 10 of x is often written as log of x. The graphs of natural log of x and e to the x look like this.
Now we're going to go into detail about the properties of logarithmic functions. When changing from exponential form to logarithmic, or vice versa, use the formulas shown here. X equals e to the y turns into y equals ln x, and x equals a to the y turns into y equals log base a of x. For example, if you have the problem change 5 cubed equals 125 to logarithmic form. The base is 5, the argument equals 125, and the exponent is 3. So to change to logarithmic form, you would make it log base 5 of 125, which is the argument, equals 3, which is the exponent. Now moving on to logarithmic properties. Logarithms have unique properties that can be used to expand or condense the functions. The different properties include natural log a times b is equal to natural log a plus natural log b. Natural log a over b is equal to natural log a minus natural log b. And natural log a to the n is equal to n times natural log a. These properties work for any bases, but only if a and b are both positive. For instance, if we have a problem expand natural log 3 times x to the 5th times quantity 7x to the 3/4, you would bring the exponent to the front and use product property. So the answer would be natural log 3 plus 5 times natural log x plus 3/4 times natural log 7 plus 3/4 times natural log x. Another example is if we have a problem condense 1/2 times natural log x plus 9 times natural log quantity x plus 3 minus natural log x. The coefficients would become the exponents, so it would become this. Natural log x to the 1/2 plus natural log quantity x plus 3 to the 9 minus natural log x. You would use product property to make it natural log x to the 1/2 times quantity x plus 3 to the 9 minus natural log x. Next you would apply quotient property. So the complete answer would be natural log quantity x to the 1/2 times the quantity x plus 3 to the 9 all over x.
Another important formula to note about logarithms is called the change of base formula. This formula is used to solve a logarithm using its argument and base. It states that log base a of x is equal to log base b of x divided by log base b of a. Since the only two logarithmic bases on your calculator are 10, which is the log key, and e, which is the natural log key, you'll change bases on your calculator in one of two ways. Log base a of x is equal to log of x over log of a, or log base a of x is equal to natural log of x over natural log of a. First example is, using your calculator, find the value of log base 8 of 649 accurate to 3 decimal places. Use the change of base formula to get this value. If a is 8, x is 649, so log base 8 of 649 is equal to log of 649 divided by log of 8, or natural log of 649 divided by natural log of 8. The answer you should get is 3.114. For our next example, we'll find x if 7 to the power of 2x plus 5 is equal to 85,902. So natural log both sides, and then simplify using log properties. You should get up to this point, 2x plus 5 is equal to 5.834. That's equal to natural log of 85,902 divided by natural log of 7. The answer you should get is x is equal to 0.417.
Welcome back. Now we're going to talk about differentiating logarithmic functions. When taking the derivative of a log function, it's a little different than taking the derivative of, say, a polynomial function. The derivative of ln x is equal to 1 divided by x, and this is obtained by taking the derivative of the argument, which is x, for the numerator, which is equal to 1, and leaving the argument as a denominator, which is just x. The same applies for if you have ln of u, but you use a chain rule for the numerator, leaving the denominator the same. For the derivative of log base a of x, that's equal to 1 divided by x times ln a. The same applies for log base a of u, but you use the chain rule instead, which means you derive the argument for the numerator. Here's an example. If we have the problem, differentiate f of x is equal to ln of 4x cubed plus 3x squared plus 4x plus 6. The first step is to take the derivative of the inside, which is equal to 12x squared plus 6x plus 4, and that's your numerator. For the denominator, you leave the inside the same, so it's just 4x cubed plus 3x squared plus 4x plus 6. And your answer is your numerator divided by your denominator, which is f prime of x is equal to 12x squared plus 6x plus 4 divided by 4x cubed plus 3x squared plus 4x plus 6. If we have another problem, such as find y prime of 1 if y is equal to log base 2 of x squared plus 1, you have to find the derivative of the argument, which is 2x, and then apply the log derivative formula. And that leaves you with 2x divided by x squared plus 1 times ln of 2. Then you plug in x equals 2, and you're left with y prime is equal to 4 divided by 5 times ln of 2. When differentiating the natural log function, if your argument is an absolute value, it may change the domain of the function, but not the derivative. For instance, if we have find the derivative of ln of absolute value 4x cubed plus 3x, it's equivalent to find the derivative of 4x cubed plus 3x without the absolute value. So the process is the same. For the numerator, you're just left with 12x squared plus 3, and for the denominator, you leave it the same, which is 4x cubed plus 3x. So your final answer is 12x squared plus 3 divided by 4x cubed plus 3x.
If you want to find the derivative of a function that has variables in both the argument and the exponent, then you need to do something called logarithmic differentiation. So the steps for this is as follows. So the procedure is to take the natural log of both sides of the equation, then simplify the right-hand side of the equation. Number 3 is differentiate both sides, then solve for y prime, and then finally substitute for y if necessary. For example, if we have this problem, find dy over dx in terms of x of the equation y equals 3x squared plus 5 to the power of 6x plus 4. First, follow the procedure for logarithmic differentiation. So our first step would be to take the natural log of both sides of the equation, and then, as you can see, simplify the right-hand side of the equation, 6x plus 4 times natural log of 3x squared plus 5. Then differentiate both sides. You get 1 over y dy over dx is equal to 6 natural log 3x squared plus 5 plus 6x plus 4 times 6x divided by 3x squared plus 5. Then solve for dy over dx. As you can see, we have y multiplied by your right-hand side. So substitute for y with the original equation, and now your answer you should get is dy over dx is equal to 3x squared plus 5 to the power of 6x plus 4 times the quantity of 6 natural log 3x squared plus 5 plus 6x plus 4, 6x divided by 3x squared plus 5.